Chapter 20, Lesson 2. In this lesson, we'll talk about balancing oxidation-reduction equations. Remember, this whole chapter is about a type of reaction that transfers electrons from one species to the other, and the species that gives up the electron is oxidized, the species that accepts it is reduced. And both of these happen. So there are many of these reactions out there, and we'll learn how to balance them. Now, balancing these is actually a little bit involved, and there are different ways of doing it. I will show you the half reaction method. This is probably the most common and the most foolproof way of balancing these oxidation reduction equations. I will go through the rules quickly, and then we'll do a few examples. So don't worry too much about understanding the rules yet. After we do an example or two, it'll make more sense. But what we'll have to do is treat the oxidation reduction process as two separate processes. Now, in truthfulness, both happen at the same time, because if a species loses electrons, those electrons must go to the other species. So these cannot occur without each other. But this will help us balance the equation. And then we'll combine them back for the overall reaction. So here are the rules for the half reaction method. First, determine what is oxidized and what's reduced by assigning oxidation numbers, which is what we did in the previous lesson. Then write the two half reactions. You're actually going to split the overall reaction into two, the oxidation half and the reduction half. Thirdly, we'll balance each half reaction in this order. We'll first balance everything other than hydrogen and oxygen. Then we'll balance the oxygen, and we'll do so by adding water. Most of these reactions will have water present in them, and oxygen serves to accept electrons or give up electrons and so forth. And then we'll balance the hydrogens by adding H+, and the H+ will be essentially from an acid. And then we'll balance the charge by adding electrons. This is something new, we haven't done this before, but we'll add electrons to the side that needs it. Then we'll multiply the half reactions by integers so that the number of electrons gained and lost equal, and this will help us balance the reaction. And lastly, we'll add them back together, subtracting things that appear on both sides, and then we'll do a little check. Make sure the equation is balanced according to mass, in other words, all the atoms are present, and make sure it's counted according to charge. Make sure we didn't lose any electrons or gain any electrons. So why don't we get to it? Let's try to balance this equation here. Now, the first step said find out who gets oxidized and who gets reduced. Most of the time, it'll be easy to see which substance goes with which. In fact, here, MnO4 will go with Mn, and then C2O4 2- will go with CO2. This is because if you take a look, if you analyze the charge of manganese here, you have 4 oxygens, each is a -2 charge, so you have a total of -8 for the charge on the oxygen side. The overall charge is -1 of the whole compound. Manganese, therefore, to balance the 8 oxygens, to get the -1, must be +7. So manganese goes from a +7 down to a +2. Manganese gets reduced, and then carbon then gets oxidized. Here, carbon has a +4 charge, and if you analyze carbon here, we have 4 oxygens, again each is -2, for a total charge of -8 on the oxygen side. The carbon then must be +6 in order for the total to still be -2, which means each carbon is +3. So we're going from +3 up to +4. Carbon is undergoing oxidation. So once we've determined which is oxidized, which is reduced, let's go ahead and split the two up. So we'll put the, I'll go ahead and do them top to bottom. Let's do manganese first. So we got MnO4 going to Mn2+, and then we've got C2O4 2- going to CO2. So this is essentially the first step, to split them up. Next comes the balancing part. Let me go ahead and rewrite them on the next slide so we have enough room to balance them, and I will probably recommend balancing them side by side, so I'll try to squeeze them in together here. Let's go and rewrite the two half reactions. So we had permanganate, Mn, let's give ourselves a little more room. So we had MnO4 minus 1 becoming Mn2 plus, and we had C2O4, a little more room, C2O4, this is oxalate, something called oxalate anion, becoming CO2. And what we'll do then is balance each half reaction. If you remember, we said let's go ahead and balance the all the atoms except oxygen and hydrogen. So in the first equation, everything is balanced except the oxygen, so we're good there. In the second equation, we have to balance the carbon, so we'll have to put a 2 in front to balance out the carbons. That way we have 2 of each. Next, in the top equation, we have to balance the oxygen. Because we have 4 oxygens on the left side and no oxygens on the right, we have to put 4 oxygens on the right. But we'll do so by adding 4 waters. That is how we actually balance for oxygen. So we'll put 4 H2O. Right away, this will add hydrogens. In fact, we have 8 hydrogens on the right side. We have to put 8 of them on the left side, and we'll do so by putting it in the form of H+. So we'll do 8 H pluses. Let's do the same thing to the second equation, and actually the second equation is already balanced because we have 4 oxygens and 2 times 2, 4 oxygens, so we're good there. Lastly, we'll have to put the electrons, and the electrons really are the key that will help us balance both of the reactions. So we have to keep track of the charge. If you take a look on the left side, the total charge on the left side is +8 from the hydrogen and -1 from the permanganate. The total charge is +7 on the left side. On the right side, the total charge is +2. That's because water doesn't contribute anything to the charge, it is neutral. We have to equal out the charge, so this is something new. And the way we're going to equal out the charge is we'll put electrons on the side that needs to get lowered in charge, since electrons are negative. So we'll actually need to add 5 electrons to the left side. So I will put +5 electrons, like this. We'll do the same thing for the bottom equation. This side is a -2 charge, this side is 0. So we will need to add 2 electrons to the right side. I'll put +2 electrons. That way I can get a -2 both on the right and on the left side of the equation. So we balance for the electrons, for all the atoms, and for the electrons. The next step is we have to get the electrons to equal out. The electrons will help us get both of these equaled out. And the way we do so is to get both of the electrons to some number that's the same. So I propose multiplying the first equation by 2. This will, 2 times 5 will give us 10 electrons. And I propose multiplying the second equation by 5. This will again give us 10 electrons. The point here is we want to get the same number of electrons. And very often you can do so by simply using the 2 numbers for the electrons, the 2 and the 5. But the point is sometimes you only need to multiply 1 to get them to be the same. So why don't we rewrite these now, multiplied out. So I'm going to rewrite this one down here. We end up with 8 times 2, we end up with 16 hydrogens. We end up with 2 permanganates. We end up with 10 electrons on the left side. On the right side, we've got 2 Mn2 pluses and 8 waters. The bottom equation, let's do the same thing to the bottom equation. Multiply by 5, so we have 5 oxalates, C2O4 2 minus. We have 10 carbon dioxides, and we have 10 electrons. Now, the last thing to do, since both of these are now balanced, what we want to do now is combine these two equations together and collapse them back down, essentially. The way to do so is anything that appears on both sides will cancel out, and anything that appears on the same side will add up, like we've done in previous chapters. The first thing to cancel out are your electrons. Notice these appear on the right side, and these appear on the left side, so they cancel out. Electrons were there to help us balance the whole equation, so we are good. Now if you take a look, everything else should stay, nothing else needs to be cancelled out. This is not always the case, as you'll see. Sometimes you'll end up cancelling out waters or hydrogens or something else, but because these are good now, let's go ahead and put them back into one big equation. So I'll combine everything on the left side of the arrow and everything on the right side of the arrow. So what we end up with in the end will be 16 hydrogens on the left side, 2 permanganates, and 5 oxalates. On the right side we have 2 Mn2 pluses, 8 waters, and 10 carbon dioxides. And this should balance the equation. Now it's a good idea to check. In fact, let's go ahead and take a look, make sure we are balanced for everything. Hydrogens, we have 16 here. We have 8 times 2, 16. Manganese, we have 2. We have 2. Oxygens, we have 2 times 4, we have 8. And then 5 times 4, that's 20. We have 28 oxygens on the left. Here are 10. And here are 20, 28. Carbons, we have 10. Carbons, we have 10. So the mass is balanced. Let's also see if the charge is balanced. If you take a look, we have plus 16 on the left side, minus 2. Let me actually keep a count of this. So this is plus 16, this is minus 2, and this is 5 times 2 minus 10. For a total charge of 10 minus 2, or we got negative 12, plus 16, we got negative 4 on this side. On the right side, if you I'm sorry, not negative 4, we got positive 4, because hydrogen is positive. This is positive 4. On the right side, these are zeros, and here we have positive 4. So notice the charge also balances. So we have correctly balanced our redox equation, and here it is. Very often they'll want you to put in state symbols, so just carry the state symbols over from the original equations. So hydrogen will be aqueous. This can be aqueous. Anything with a charge will be aqueous. This will be aqueous. So will this. Manganese 2 plus will be aqueous. Water will be liquid, and CO2 is a gas. And you are set. So we're going to do one more balancing, and this one, the reaction that we just balanced, was balanced under acidic conditions. And that's where we added the hydrogen plus. It's possible, it turns out, to also balance reactions in basic conditions. And many batteries actually run in basic conditions. Your car battery runs under sulfuric acid conditions, so it's an acidic based battery. Most of your handheld batteries that go into any sort of small electronic device are usually basic, and that's what the word alkaline means. It means basic. So the difference between balancing an acid based and a basic redox reaction is just one more step. So here's what the additional step would require. If a reaction occurs in basic solution, and we'll have to be told when it occurs in basic because you can set it up either way, first balance it the same way we just did, as if it occurred in acid. And then once it's balanced, we're going to have to neutralize the acid by putting hydroxides. This should say OH minus. By putting hydroxide to each side to neutralize the H plus. Now this will create water, and that water will have to be cancelled out from both sides. Again, let's do an example, and this hopefully will become a little more clear after we do this example. So we're asked to balance this reaction now in basic solution. Let's go ahead and balance it in acidic solution as we've done before, and then we'll convert it to basic solution. The first thing we did is took a look at the charges. This is a good exercise. So if we take a look at the carbon here, the nitrogen has a minus 3 charge usually. Well, in this case, actually, the nitrogen will probably be a little different in Cn. So we'll assume that the actually, in this case, the first step of assigning oxidation numbers isn't necessary. So this will actually just complicate things a little bit. We could keep track of them, but we realize that Cn must go with CnO minus, and MnO4 must go with MnO2. So we can actually write out our half reactions as Cn minus becoming CnO minus, and MnO4 minus becoming MnO2. You know these go together. If you're asked which one's oxidized, which one reduced, well, you can take a look at the oxidation number of manganese, balanced by 4 oxygens. Oxygen is -8 again, so manganese must be +7, and here manganese is +4. So manganese gets reduced, and then carbon must get oxidized. In fact, carbon does get oxidized. Whatever carbon's charge here was, it's 2 more here, since we had to add 2 oxygens. I'm sorry, we had to add oxygen, which has a charge of -2, to increase carbon's oxidation number. So whatever it was, it gets a +2. So you can say that carbon used to be +4, which means nitrogen would be -5, and then here carbon is +6. But this isn't as important, but we do see that carbon gets oxidized either way because of the addition of the oxygen, and that technically is where the idea of oxidation came from. It's the addition of oxygen, which provides negative charges, which means that species must have increased in charge. Okay, let's go ahead and balance it like we did the last one. Let's rewrite our 2 half reactions. In this case, Cn minus going to CnO minus, and MnO4 minus going to MnO2. Let's first balance each equation for all atoms except hydrogen and oxygen. The first one is already balanced. We have a carbon on each side, we have a nitrogen on each side. The second one is also balanced, a manganese on each side. Let's go ahead and keep balancing first for the oxygens. On the first one, we'll have to add to the left side a water, because remember the way we balance for oxygen is by adding water. So we have water on the left side here. This introduces 2 hydrogens, so we'll have to put 2 hydrogens plus on the right side. And thirdly, we have to balance for the charge. And the charge, again, is balanced by putting electrons. So on the right side, if you take a look, we have -1 plus 2 for a total charge of +1. On the left side, we have -1. So we'll have to add 2 electrons to the right side to balance them out. That way, both sides have a -1 charge. Let's do the same thing for the second equation. We need 2 more oxygens on the right side, because we have 4 on the left, 2 on the right. We'll add 2 waters to the right side. That introduces 4 hydrogens. Let's go ahead and put 4 hydrogens on the left side to counterbalance it. And now looking at the total charge, +4 here, -1, that's +3. This is 0, so we need both sides to be 0. Remember, we're going to add electrons to the side that needs to get reduced. So which side needs to get reduced? This is the left side, and we'll put 3 electrons on the left side. Plus 3 electrons. Next, if you recall, we multiplied each equation by a number to make the electrons equal. So why don't we multiply the top one by 3 and the bottom one by 2. This will get both half reactions to have 6 electrons. Let's then go ahead and rewrite them. So for the top one, we have 3 waters plus 3 cyanides, giving you 3 CnO minus, 6 H pluses, and 6 electrons. For the second equation, we'll have 6 electrons. Notice again, electrons are the same, plus 8 hydrogens, plus 2 MnO4 minus, producing 2 MnO2s and 2, whoops, not 2 but 4 waters. 4 H2O. At this point we can start canceling out what appears on both sides, always beginning with the electrons. So the electrons cancel out. Next, here we see that the hydrogens can also cancel out, appearing on both sides. So these 6 will actually cancel out with 6 of these, leaving you with 2. So we will have 2 hydrogens left. Likewise, water, 3 of these waters will cancel out with 3 of these, giving us just 1 water left. And the rest should stay. So let's go ahead and rewrite this into a full equation, just like we did previously. So we've got 3Cn minus plus 2 hydrogen pluses plus 2 permanganates, giving us 2 MnO2s and 3CNO minus, as well as a water. Make sure we've accounted for everything. This should work. And now we can actually convert them into, before we do the last step, this is now balanced in terms of acid. In fact, if you take a look, we have H+. This is what tells us that the equation is balanced in terms of an acid. Let's go ahead and see if we're balanced both charge-wise and mass-wise, and then we'll convert it into base. On the left side we have 3 carbons on the right, 3 nitrogens on the right, 2 hydrogens on the right, 2 manganese, 2 times 4, 8 oxygens. We have 4 here, 3 here, that's 7, 1 more, 8. We're good on the mass. Let's take a look at the charge. We have a -3 here, a +2 here, and a -2 here. The +2 and the -2 cancel each other out for the total charge on the right side of -3. So we have -3 on the right side. On the left side, I'm sorry. On the right side we also have, this is 0 and this is 0, we have a -3. So we know we are balanced, both charge and atom-wise. Now to convert using base, to convert to the basic version. It is as simple as adding hydroxides. And how many hydroxides do we add? However many hydrogens there are. So since we have 2 hydrogens, let's go ahead and add 2 hydroxides. Now when you add 2 hydroxides, you must do it to both sides, otherwise it will not be balanced. To keep it balanced, we must add 2 hydroxides to both sides, and that's exactly what we'll do here. These two will combine together. Hydrogen and hydroxide is like an acid-base neutralization reaction to give us 2 waters. And then furthermore, since we have waters on both sides, we'll have to cancel out this water. This water gets cancelled out with one of these waters, and we're left with 1 water. And let's go ahead and clean it up by rewriting everything now in basic form. So we have 3Cn minus plus a water plus 2 MnO4 minus, giving you 2 MnO2, 2 hydroxides, and 3 CnO minus. Notice now we have hydroxide in our reaction instead of hydrogen like we had before, and so this is now balanced for basic solution. We can also do a quick little check just to make sure, but we should remain balanced. 3 carbons, 3 nitrogens, 2 hydrogens. This 2 got away from us. 2 hydrogens. We have 2 hydrogens here. Here we have 1 oxygen plus another 8. That's 9 oxygen. 4, 5, 6, 7, 8, 9. The charge we have -3, -2 for a total of -5. -2, -3 for a total of -5. We are balanced in basic solution. So we've shown you 2 examples of how to balance redox reactions. We'll practice some of these, and that way you're able to balance these. This concludes lesson 2 of chapter 20.